Greetings. My name is Fanro Chong, and I am from the University of Tsukuba. Today my presentation will be about a study of FPGA-based cluster computing with high-speed serial links. Here is the outline of my presentation. We will begin with the backgrounds. This is a graph of some important trend data in the field of microprocessors from the 70s till the year 2018. With the increasing needs of computational power, the performance of processors is also growing at a high speed. Till 2005, this growth is mainly achieved with the improvement of single-core performance, or the frequency. After the same year, the trend shifted from improving the single-core performance towards increasing the number of cores. This is because that the density of elements on a chip has nearly reached the physical limit, and further improvements will be very difficult. It is also at this time that more large-scale clusters are built, in which the internode communication becomes a main factor that affects the overall performance. On the other hand, another way of improving a system's performance or power efficiency is to not add extra number of the same type of processors, but dissimilar coprocessors specialized to handle a certain kind of tasks. This is also called heterogeneous computing. The most used heterogeneous processors are GPGPU, FPGA, and DSP. On the screen is a node diagram of the supercomputer Cygnus installed at the University of Tsukuba. Cygnus is the world's first GPU FPGA-equipped supercomputer to be opened for public use by various fields of application users. In the diagram, each FPGA has 4 end-to-end communication channels to another 4 FPGAs with high-speed serial links. Our research will dig more deeply into these HSS links and the FPGA network. There is a prototype of Cygnus called PPX, which is also a heterogeneous system of CPU, GPU, and FPGA. For its FPGA part, experiment results considering computation and communication have been reported by Mr. Fujita's work. Mr. Fujita's research implemented an OpenCL version of Himeno Benchmark and tested it on 4 nodes on PPX. His system connected the FPGA nodes with HSS links, and the benchmark score was 22.7 gigaflops. This was an excellent work, but we believe there are still possible improvements. First, the system can be implemented in hardware description languages instead of OpenCL, which allows us to more accurately control the details of the system. Moreover, we can extend the HSS links and implement a router over it, making it allow larger FPGA networks. With these improvements, we can achieve a higher performance than the related research. These are the main objectives of our research. This is a simplified graph of the high-speed serial link on QSFP modules, which is used in our research to connect FPGAs. The quad small form factor pluggable modules of 2 FPGAs are connected to each other with an optical cable. This interface supports up to 100 Gbps data transfer, which is much higher than the clock frequency of normal FPGA chips. To match this high speed, FPGA boards usually come with the gigabit transceivers, the GT. In our system, the communication between GTs is controlled by the Aurora protocol. The Aurora IP core, provided by the FPGA vendor, serialize and deserialize the data and send status information to maintain the link. This link only supports peer-to-peer communication. One of our main goals is to improve this. Usually, the user application controls communication IPs directly when sending data. We add an additional router module between the user application and the Aurora IPs so that the user only needs to decide where a data packet is targeting, and the actual path the packet takes depends on the router and is transparent to the user. Here is the details about the router. The Aurora data stream is formed with 256-bit frames. We add a header frame before the data frames to carry necessary information for the router, including the packet size and the address of the target node. The outgoing data stream is represented with blue arrows in the figure. The router reads information in the header and decides from which channel the packet will be sent. And on the receiver side, the router reads the header of an incoming packet, which is the black arrows in the figure. It holds the packets targeting itself, the orange arrows, and forwards the other packets, the green arrows. Note that the source address is not included in the header. It also does not mark the order in which packets are sent, and by default, the receiver does not return a confirmation to tell the sender a packet is correctly received. In our system, no end-to-end connection are established. This is for efficiency purpose, and it is also possible for the user to do this with a higher layer protocol. There are unused bits in the header marked reserved in the figure. This field can also be used to carry additional information. In the proposed system, each Aurora IP is linked with a transmit buffer and a receive buffer. When the transmit buffer is full, a signal is asserted, and the router will stop trying to send packets from this channel. The situation is a bit more complicated with the receiver buffer because it must inform the Aurora IP in another FPGA node about its status. This is done by sending a native flow control message through the Aurora channel. NFC messages are of the highest priority and will be immediately transferred. However, it still takes some time to encode and decode the message, so there is a latency till the message is received. To deal with this, we configure the receive buffer to send the NFC message not when it is full, but when the space is occupied over a certain threshold. When the network is busy, it is essential to make good use of both channels to improve the effective bandwidth. In our research, a load balancing mechanism is implemented in the communication circuit to improve the performance under heavy load and prevent traffic congestion. On the screen is a figure of how this mechanism works. Let's say a packet is sent from node A to node C. Usually, this packet will take the path ABC, for this is the shortest. However, when this path is unavailable, for example, when node B is also sending packets to C, it will be better for packets from node A to go through another path. In this example, when the channel BC is busy, the receive buffer of channel AB will also be occupied following the procedure discussed in the previous page. The blue arrows in the figure shows this process. After that, packets from A will be sent to channel AE, which is painted orange in the figure. This will increase the overall effective bandwidth. Next, I want to talk about the performance evaluation in our research. we focus on the stencil calculation that is widely applied in physical simulations and many other scenarios. The stencil calculation is often sensitive to the memory bandwidth, thus is very suitable for the FPGA. In our research, we used the Himeno benchmark. The benchmark solves Poisson's equation using the Jacobi iteration method, as shown in the figure. In each iteration, to calculate the next state of the red point, 18 adjacent points painted yellow in the figure is also needed as input. The Himeno benchmark is standardized in different sizes for fairness. Unfortunately, the Himeno benchmark is only provided in C and Fortran for CPUs. Since no HDL version exists yet, we have to implement it by ourselves. This picture shows the core part of the Himeno benchmark. Every iteration of every point contains 34 single precision floating point operations. There are 13 parameter matrices in total, so the required memory space for each size can be calculated as shown in the table. Taking the available amount of memory on our FPGA boards into consideration, we will implement the S size, which requires 26 MB of memory. This will fit into the block memory of the FPGA chips used in this research. Therefore, we will not use external memory, but only block memory in our system. We divide the problem space in all three dimensions, making 8 subspaces. These spaces are assigned separately to the 8 FPGA nodes in the system. We code the addresses of subspaces in reflected binary, so that the whole space is symmetric, and the node can infer another node's relative position from their addresses. Since the space is divided and every point must access its neighbors, inevitably some points will have to access points located in another FPGA node. To solve this problem, nodes send out these parts of data that are needed by other nodes after every iteration. The figure shows these parts of points of the upper left rear subspace. The gray points are not sent to any other node, and the yellow points are sent to only one node, the orange ones to 2 nodes, and the red point is sent to all other nodes. Only one matrix is involved in this transfer, so the total transfer size of every iteration is 20.5 KB. When calculating the next state of the space, we shift a 3-layer cache window through the whole space. We keep 3 continuous layers in the window at all times, and shift the next layer in when the calculation of the middle layer is done. When calculating the middle layer, 256 processing elements run 4 times from up to down to complete the whole layer. The results are then written back to the memory before the next layer is loaded. Here is the diagram of the structure of the processing element. The FPGA chip we used is equipped with a kind of arithmetic logic unit called DSP48. In our system, we use these units to do floating point operations. Every 2 DSP48 can be configured as an adder, or a multiplier. Our processing element contains 3 adders and 2 multipliers, consuming 10 DSP48. These 5 operators read hard-coded instructions and perform operations on results registers. It takes 22 clock cycles for them to iterate 1 point. Combining the different parts that we discussed, the Himeno benchmark on FPGA is implemented. Here is the system structure diagram. The Himeno benchmark solver and the communication module discussed earlier are combined and programmed into our experiment device, the KCU1500 board. We use 8 of these boards to form a ring network and evaluate the performance of the proposed system with a series of experiments, including the latency test, the throughput test, and the functionality test. We also tested the Himeno benchmark score of the proposed system. We first tested the latency of the end-to-end HSS link. Results show that every node in the transfer path adds approximately 227 nanoseconds of latency onto the packet. We then tested the throughput of the HSS link. The results are shown in the graph on the right. The gigabit transceivers on the FPGA board we use support up to 40 Gbps data transfer. The actual result is a little lower than this because the Aurora IP core also sends handshake messages to maintain the link. When the transfer size is small, this overhead is very big, but its effect is weakened with a larger transfer size. This is the functionality test of the routing and the load balancing. In this case, we discussed earlier, packets from A can be sent to C from both paths. The pattern shown in the graph is observed, which validates the functionality of routing and load balancing. Results show that our system has increased the effective bandwidth of the host network. We also tested the computation performance of the proposed system. The Himeno benchmark server of our system runs at 100 MHz, and the communication module runs at 200 MHz. We measured the time consumption from the calculation part. The result is shown in the figure. With this data, we can calculate that the total performance of the 8 FPGA system is 240.6 gigaflops, and that of one FPGA is 30.08 gigaflops. This table shows the resource consumption of the proposed design on our FPGA device. The utilization ratio of DSP is smaller than 50%. This implies that further improvement is possible by doubling the number of processing elements. In conclusion, we developed a network framework for FPGA clusters using hardware description language instead of high-level synthesis, and we evaluated its performance. The results show that the routing function makes it easier to transfer data in systems with more FPGA nodes, and the load balancing function increases the total effective bandwidth. It is possible to better utilize the excellent communication power of FPGAs and solve problems that require a greater amount of memory space. And there is still unutilized communication capability of the FPGA board used in this research, such as the PCIe ports. Further improvements are possible. Thank you for listening.